in our last video, we argued that geometry, that's right, that annoying section of mathematics from your days in elementary school, is in fact the entity responsible for setting all of the most important rules in the universe, namely the laws of conservation. To inspire this fact, we introduced the concept of symmetry, which we may now broadly define as the observation that some aspect of a system does not change even when the system is acted upon in some way, for instance, through a rotation or a translation. We then noticed that imposing such a symmetry must constrain the possible configurations of the system, and therefore maps perfectly onto our notion of the laws of conservation, which similarly constrain the set of possible state transitions observed in nature. Finally, we gave a concrete example, the symmetry of the laws of nature under translations in space and time, which resulted in the conservation of energy and momentum. In this video, we'll introduce one of the most powerful theorems in all of physics that makes this relationship between symmetry, on the one hand, and the laws of conservation, on the other, absolutely explicit. That is Noether's theorem. Noether's theorem states, for every continuous symmetry of the action of a physical system, there is an associated law of conservation. Let's unpack exactly what this means. First, remember our old friend, the action, the integral of the Lagrangian over time. It dictates the rule for how a system progresses from its initial state of being to its final state. In this way, the action governs all of the physics of a given system. So, when we say the action of a physical system, we might equivalently just say the laws of nature governing it. Next, let's tackle a continuous symmetry. A symmetry, we know, is just an aspect of the object that we're analyzing which is unchanged under the action of some transformation. A symmetry is continuous if the transformation generating it can be applied in a continuum of different ways. Take, for example, the rotation. A rotation of a system refers to rotating that system by any number of degrees, ergo a continuum of different possibilities. We can rotate by 100 degrees, 10 degrees, 76 degrees, any real number. Putting these two things together, we can restate Noether's theorem as follows. For every way a physical system can be changed through a continuum of possibilities without altering the underlying laws of nature governing the system, there is an associated law of conservation. Put in this way, the logic of Noether's theorem is precisely what we suspected all along. If the laws of nature are unchanged when a system is acted upon in some way, Mother Nature loses the ability to uniquely define a corresponding aspect of the system. All that remains is to determine what aspect is related to what symmetry. Amazingly, Noether's theorem not only tells us that a conserved quantity exists, but it provides us with a computational method for determining what conserved quantity is associated with a given symmetry. The actual business of computing this conserved quantity is quite tricky, but the basic idea is this. Recall that the action is a sum of the Lagrangian over all times, and that the Lagrangian is itself built from the quantum fields of particles present in a given system. Performing some transformation on the system will therefore define the following chain of events. Firstly, the quantum fields will change in some way due to the transformation. Secondly, the Lagrangian will change in some way due to the transformation, and, since the Lagrangian is a function of the quantum fields, due to the change in the quantum fields. Lastly, since the action depends on the Lagrangian, and the Lagrangian depends on the quantum fields, when the quantum fields change and the Lagrangian changes, the action too must change. It turns out, mathematically, that the change to the action at each time can be thought of as the flow of some quantity. If our system is invariant under some transformation, we know that the total change to the action must be zero. That is to say, the total flow of the quantity is equal to zero. This implies that whatever quantity is being described cannot be created or destroyed. It comes in a fixed amount. That is to say, this quantity is precisely our conserved quantity. The importance of Noether's theorem cannot be overstated. Not only does it place the relationship between symmetry and conservation on firm footing, it provides an approach for computing all of the conserved quantities associated with a given system. In the next video, we'll begin to apply Noether's theorem in order to derive the fundamental conserved quantities of the standard model. But until then,